We've looked at the core features of trigonometry, covering the sine, cosine and tangent functions, and introduced the concepts of radians as a measurement of angle. These have numerous applications in chemistry, but the last area of trigonometry we should look at considers the use of coordinate systems. We use coordinate systems extensively to specify positions, locations and directions. In 2 dimensions, we use the horizontal and vertical directions to specify the position of a point. This can be extended into 3 dimensions by adding a third axis. This coordinate system is called a Cartesian system, and all the variables are typically x, y, and z. These are used all over the physical sciences, and in particular when plotting experimental data, as it makes it very easy to visualize how 2 or even 3 interrelated variables correlate with each other. However, there is a second coordinate system that we should be aware of, and this is called the polar coordinate system. In a nutshell, rather than saying a point is defined as 3 steps in one direction, 4 steps in another, the polar coordinate system tells us that a point is defined as face a particular direction, an angle, and take 5 steps in that direction. We are then defining our point by an angle from a reference line and a distance from the origin, a so-called r theta coordinate for radius and angle. In 3 dimensions, called spherical polar, we use a radius and 2 angles, the polar angle and the azimuthal angle. By convention, the reference line for polar coordinates is in line with the x-axis in Cartesian coordinates. This may seem like an odd system to use for experimental data, but it has a very important application in chemistry. As a quick introduction to polar coordinates, think of a circle. The equation of a circle in Cartesian coordinates looks unusually familiar. R squared is equal to x squared plus y squared. So for a circle of radius 2, the equation is 2 centimeters squared is equal to x squared plus y squared. Of course, its roots are naturally in Pythagoras' theorem, but remember that r is fixed. This means that x and y cannot vary independently, so while it looks like we have 2 variables, in reality we only have 1 degree of freedom if we want to describe a circle. If x is allowed to change freely, then y is bound to a particular set of values, otherwise we will not get a circle. We can describe a circle much more easily in polar coordinates. For the same circle of radius 2 centimeters, the equation is simply r equals 2 centimeters. Most chemistry students are familiar with the shapes of atomic orbitals. However, the manner in which their shapes come about are much easier to picture when we think in polar coordinates. It's easier to picture this by thinking of a more apparent polar coordinate system, namely the lines of longitude and latitude which cross our planet. We can define the position of cities relevant to specific reference angles. The first of these is the equator encircling the planet, the second is the vertical prime meridian, which, by convention, was defined at Greenwich, London, lying at 51.4 degrees north, 0.0 degrees east. By comparison, Greenwich Village, New York, lies at 40.7 degrees north, 74 degrees west. In an atom, we can define the position of an electron using similar polar azimuthal angles. However, the twist comes when we think about the radius. When we think of our position on our planet, we don't tend to consider the radius, the distance from the centre of the Earth, because, unless we are airline pilots or building tunnels, we only navigate across the surface. However, think about energy changes as we fly in a plane. We have kinetic energy as the plane flies forward, i.e. its longitude and latitude is changing, but we also have gravitational potential energy as the plane climbs, when its radius changes. This way we fully separate the kinetic energy and the potential energy by using angular and radial components. The same is true for electrons. The potential energy of an electron in an atom is related to the radial component of the orbital, while the kinetic energy of the electron in an atom is related to the angular component of the orbital. And this is the key application of polar coordinates, which we cannot do so readily using Cartesian XYZ coordinates. To visualize polar coordinates effectively, we need to be able to interconvert between Cartesian and polar coordinates. Let's imagine a point S. This is defined in Cartesian coordinates as 2, 2. What then is its polar position? We can work out the radius using Pythagoras' theorem. Remember, it's a right-angled triangle, as the square root of 8, or 2 root 2. We can also see that this is an isosceles right-angled triangle, so the angle must be 45 degrees. Alternatively, we can say that phi is equal to the inverse sine of 2 over 2 root 2, which is equal to 45 degrees. Or phi is equal to the inverse tangent of 2 over 2, again 45 degrees. Let's now consider point U in polar coordinates at a radius of 5 centimeters and an angle of 53 degrees. How do we convert this back to Cartesian coordinates? Well, remember again we have a right-angled triangle, so let's look at our sine-cosine formulae. The x-coordinate is adjacent to the angle, so we use the cosine function. X is equal to r cosine of phi, which is 5 times cos 53, which is 5 times 0.6, which is equal to 3 centimeters. We can do the same thing for the y-coordinate, but it's now the opposite side. So we use y is equal to r times the sine of phi. 5 times sine of 53, 5 times 0.8, which is equal to 4 centimeters. Finally, let's now consider point V, again a radius of 5 centimeters, but now at an angle of 143 degrees. It's tempting to think that there is a right-angled triangle now, but on the negative side of the x-axis, necessitating a calculation to determine the angle of interest. However, let's just look at what we did before and apply the same formulation. We said before that x is equal to r cosine of phi, while y is equal to r sine of phi. Let's apply this and see what happens. X becomes 5 times minus 0.8, equal to minus 4 centimeters, while y becomes 5 times plus 0.6, which is plus 3 centimeters, giving us the correct coordinates. The reason this works is by going back to the cyclic plots of the sine and cosine functions. If we relate this to a Cartesian plot, remember that x is equal to r cosine phi, while y is equal to r sine phi, we can see what happens to each of these in each quadrant of the Cartesian plot. Between 0 and 90 degrees, we would expect both cosine and sine functions to return a positive value. Between 90 and 180, we would expect cosine to return a negative value, so it giving us that negative x-coordinate, while sine returns a positive value for the y-coordinate. We can continue this all around the Cartesian plot, and each time we get the correct positive, negative direction for each of the Cartesian points. The area of polar coordinates is rich, and we will keep coming back to these concepts through the course, but this should give a foundation for you to refer back to as we go through our explanation of these concepts. As ever, leave a comment below for questions, comments, suggestions, and we'll continue the story in our next video.